Lecture 25. Lecture 25, topic of Lecture 25 is dependability. So you can see in our class we have the Lecture 25 and Lecture 26. In Lecture 25, systems and fault tolerance is the topic. So far in this course, we can see in computer science, we want to know how to work, how software work, how hardware work, how computer combine software and hardware. This is a difficult problem. Now, what happens when the real world gets involved? Things break in mysterious ways. We can count on things breaking. So we can see this is the problem in our course. How can we ensure the systems we have developed function reliably in the face of failure? So we can see this is the management solution of fault tolerance and mitigation. So dependability is the solution, is the measurement, redundancy, and error correcting. So in dependability, we can see we can avoid the build a strong system. And the redundancy is replication. We can make copies of your important state or information so that if it breaks, you can use a replication. So replication is very useful. Error correcting, if we do incur some damage, how can we find the problem, fix the problem? So sometimes we want to duplicate or redundant or have redundancy. Okay, there are three sections in Lecture 25. One is dependability, two is error correcting code. ECC is error correcting code. 3 is RAID. Okay, we must know what is dependability. Dependability is a component or system is considered highly dependable if it is highly predictable or has a low probability of service outage. You can see unlikely to encounter failures or recover quickly when failures occur. The dependability of a system is determined by the overall dependability of its components. So we must create, we must create the dependability of a system. In computer organization, system architecture is very important in the future. A system has several components. Every component has every architecture. So the dependability of a system is very important for the system. So if you and if we have a chance to protect and relax and complex system, we must care about every component, every dependability of components. So dependability is very important in the whole system. This is dependability. There are two sections, two important points. One is fault, one is repair. What is fault? Fault is failure of a component. We may or may not due to system failure. applies to any part of the system. Repair is another point, the act of restoring normal service after a fault. So if we have fault, we don't care. We don't worry about their faults. We want to repair their faults. So you can see service accomplishment is service delivered as specified. Service interruption is deviation from specified service. So recovery and the failure are two important creation or procedure. So if we have failure, we must have recovery. Dependability measures, we can say reliability is mean time to failure. MTTF is mean time to failure. Mean time is average time. Service interruption is mean time to repair. MTTR is mean time to repair. So in this, mean is average too. Okay, mean time between failure and MTBS is MTTR and MTTF. So we must add reliability, and the service interruption. The two times. The summary of two times is MTBF. Okay, ability equal MTTF divide MTTF add MTTR equal MTTF divide MTTF. So we want improve availability. We can increase MTTF. We can reduce MTTR. So more reliable can protect fault tolerance, improve tools and process for diagnosis and repair can reduce MTTR. So we find MTTR is in this position, MTTF is in this position. We can see if we increase MTTF or reduce MTTR, the availability can increase. Reliability measures, MTTF and MTBF measures in hours per video. For example, average HDD MTTF is 100,000 hours per video. So we can see hours increase, the reliability increase, because hours is in the above. AFR analyzed video rate equal average rate of videos per year. So you can find AFR equal 8,760 hours per year divide MTTF. So you can see AFR, we want to increase AFR or reduce AFR. We want to reduce AFR, we can increase MTTF. Okay, this is another availability measure. Availability equal MTTF divide MTTF as MTTR, usually written as a percentage. We want high availability, so categorized by number of night seconds of availability per year. So you can see this number from 36 days of repair per year to 5 minutes of repair per year. So you can see this is 90%, this is 99.999%. So this number is more than is more than 90%. So if the percentage is more than 1/9, we find the time has reduced. Dependability example, we can see 1,000 disks with MTTF and MTTR. We can see MTTF is more than MTTR. So if you have MTTR, for example, this is 100,000 hours is MTTF. 100 hours is MTTR. So 100 hours is a small number compared for 100,000 hours. So MTTR is a little, MTTF is big. So you can see blue has little section, little slice. Most of times are MTTF. So we can see from left to right, we have 300,000 and 300 hours. 300,000 hours are MTTF. 3 hours are MTTR. Yeah, so this is small and little. Dependability example, we can see 1,000 disks with MTTF and MTTR. So this is the availability. This is 99.9%. This is a very big, nearly 100%. We can calculate MTTR example. The MTTR is faster test to get 4 nines of availability. The goal is close to 1% or 100%, and the smaller MTTR. So if the MTTR becomes small and small, the result becomes nearly 100%. Okay, this is dependability design principle. There are 3 principles. 1 is no single points of failure. 2 is dependability category of Amata law. In 2013, Google had 99.978 availability for their cloud cluster. Okay, there are questions. There's a hardware glitch in our system that makes the mean time to failure increase. Are the following states true or false? True. Our system ability will increase. Our system analyze failure rate will increase. This is 2 questions. Okay, we can see. In this solution, availability, this is availability calculation. As MTTF shrinks, our fraction is outweighed by MTTR. So we can see if this is MTTF, this is MTTR, this is MTTF. So if the MTTF decrease, the result, the availability decrease. Yeah. So availability decrease because the MTTF decrease. So the answer is ST. Okay, this is dependability. We can see another error correcting code, ECC. We can see this is dependability by redundancy. We can see redundancy so that a filling piece doesn't make the whole system fail. Okay, we can see this is dependability by redundancy. Redundancy is very useful. In database, in big data, redundancy is in several circumstances. We can see we can apply everything from data center to memory. So data center is like warehouse. Data center has several cluster servers, data servers. So we use cell phone because the communication companies have several database servers. Our dialogue, our message can store in these servers. So we must care the message, because in China, our secret message easy to share to internet, to every other circumstances. So we must care about the secret of message. Redundant data center, so that can lose one data center, but internet service stays online. Internet is very useful because we can see in cell phone, in laptop, in computer, we can use internet by Wi-Fi and Ethernet. Redundant loops, so can loops node, but internet doesn't feel. So the internet is powerful. We find the structure of internet is very complex. Because the complex structure of internet, we can say redundant loops is useful. Loops is something from routers. In your computer network course, router is a very useful, very important term. Redundant disks, so that can lose one disk, does not lose data. So if we lose some disk, the data center has several disks. So the data in the server has useful and hadn't missed. Redundant memory disks also that can lose one bit, but no data. So this is error correcting code. This is ECC memory. So you can find this is one disk. There are several disks. So this is some data center. Okay, this is error detection or error correction code. ECC, error correction code. Memory systems generate errors. We can see DRAM store very little charge per bit. DRAM is the main memory. So errors occur occasionally when cells are struck by alpha particles or other environmental aspects. Hard errors occur when clips permanently fail. Hard errors is hard to fix. Soft errors is easy to fix. Problem gets worse as memory systems get denser and larger. This is error correction code. Okay, we can see EDC is error detection code. ECC is error correction code. Protect against errors with ECC. Extra bits are added to each n-bit data chunk to produce an n-bit code word. So this is some method. Okay, this is ECC concept. We can see detection and correction. Detection is to field code word validity check. Correction can map to near valid code word. So we can see in the image. This image is space of all possible bit patterns. The green circle and the red circle. The green circle is correct.
Delete.
Yeah. The red circle is arrow. So you can see arrow changes bit pattern to an invalid code word. This is this section or this action. Correction is fix invalid code word back to valid. So the green circle is valid. The red circle is invalid. So this action we call correction or fix. Fix is very useful action. Okay, this is having distance. Having distance is a famous algorithm for computer network, for computer optimization. You can see having distance in what size are search engine. In Baidu, in Google, the distance, the examples of having distance have several demos. If you have interest, you can search having distance or improved having distance by search engine. But in Baidu, you search Chinese version. If you use Google, you can search English version. Having distance, the use of having distance overall is detect one big error and fix one big error. So you can see if all code words are valid, then mean HD is having distance between valid code word is 1. Change one bit to another valid code word. So we use having distance can detect one big error and fix one big error or one big correction. So this is the use of having distance. So if you have interest in details, you can search having the example of having distance in search engine. There are no distance. There are no examples or demos. Why does this matter? If the entire space of possible code words is valid, we can't tell if our word has errors. So maybe it's merged into another valid word. If some words are valid and others are invalid, we can detect errors. The detection of errors is very difficult. If some paper has some errors, you won't find these errors in this paper or in this document. You must read all the paper or documents and use your idea to judge the correction and the failure. So if you want to detect errors, you must know more and more knowledge or information. So in computer network, if the transportation has errors, we check, we choose, repeat. There is useful tragedy. Useful method. If there are a small subset of valid words and a large subset of invalid words, we can trace our error and reverse them. Okay, there is 3 bits visualization aid. We want to be able to see having distance. We can for 3 bits show each bit into a different dimension. This is bit 0, bit 1, and bit 3. There are 3 dimensions. So this is 3 dimensions mathematics. Okay, we can see if 1 bit error is code word still valid, the answer is no, so can detect. If 1 bit error know which code word we came from, solution is no. Encryption, so can cut correct. So there are some circumstances we can't correct either or for the circumstances. Okay, this is parity bit. Yeah, we know. Describes whether a group of bits contains an even or odd number of ones. Parity bit can add the parity bit to a group will always result in an even number of ones. Okay, parity is simple error detection coding. So this is some parity examples. There are some parity examples we can see. Okay, this is how to correct 1 bit error. 1 bit error, the correction of 1 bit error is simple. If the original number is 1, the correction is become 1 to 0. If the original data is 0, we can correct 0 to 1. Because the binary has 2 circumstances, from 0 to 1. So the correction of 1 bit is simple. But if you have several bits error, you can find this is difficult fiction. If you have 3, you have 8 choices, a choice. If you have 4 bits, you have 16 choices. There are more and more choices for the correction. So 1 bit error we can fix, but 2, 4, 8, there are too many choices. Okay, having ECC, we can see this. There is having ECC. There is some example we don't get. Okay, we can see the section 3, read. Read is very useful technology in data center or database. Read is redundant, array, or inexpensive or independent disk. So what is read? R-A-I-D. This is read. Yeah. So we call read because the read is redundant array of inexpensive or independent disks. So the characteristic is inexpensive and independent. Inexpensive is very important because the rate is cheap, not expensive. Files are shared across multiple disks. Now we can see concurrent disk successes improve throughput. Redundancy yields high data availability. Services still provided to user even if some components fail. Content reconstructed from data redundantly stored in the array. We can detect when data is corrupt. We can fix data correct version like before. but bit is now disk. So the read has several terms. Read 0 is the simple read. Read 0 is data streaming. So you can see stream data across all disks. Generally faster accesses. No redundancy. So the read 0 is very simple. It's very simple strategy. Read 0 can't tolerate any fields. So read 0, the ability of read 0 is very simple and very low. Bit stripping show here can do in large chunks. So you can see start physical record, data stripping. So this is no redundancy read. This is read 0. You can see every section has different sections. No duplication. No same section. So read 0 is a simple read. Okay. Read 1. Read 1 is disk mirror. What is mirror? Mirror is copy.
Copy.
Yeah. So we find we have read 1. We have 2 sections, 2 duplications. Each disk is fully duplicated onto its mirror. There is very high availability can be achieved. So duplication is very useful strategy. Bandwidth sacrifice on write. You can see logic write and logic read equal 2 physical writes, 1 physical read. Most expensive solution is 100% capacity on the head. So read 1 is disk mirror. Disk mirror is complex and expensive, but there is effective strategy. So you can see this is read 1. The left and the right have the same
mirror.
Yeah, there are mirrors.
Yeah.
Okay, read 2 and read 3 and read 4 equal data streaming and parity. So we can't use read 1 mirror, then mirror. We use read 2, read 3, read 4. Logic data is trickled, striped across disks. 2 is bit, 3 is byte, 4 is block. Bit is small, byte is middle, block is big. Parity disk P contains parity of other disks. If anyone's disk fails, we can use other disks to recover data. We must update parity data on every write. Okay, this is read 4. You know there are 4 disks, and you can see 1, 2, 3, 4. 1, 2, 3, 4. So you can see read
That one
is like read 0.
Yeah. That one is parity disk.
Yeah.
The right side.
There are no mirrors. Okay, we can update the parity data. But we can then small write in read 3. 1 logic write equal 2 physical read and 2 physical writes. So there is some correction and some calculation. Okay. Inspiration of 4 read 5 when writing to a disk need to update parity. Small writes are bottlenecked by parity disk write to B0, B5, but also write to P this twice. There are ones. Okay, please remember read 5. Read 5 is very useful and very popular in data center. Read 5 is interleaved parity. You can see read 5 has independent writes possible because of interleaved parity. So the red circle, the red rectangle, you can see D0, D5, PP, and the green rectangle PP is in this column. So increased logic disk addresses is in the disk column. So this is read 5. Now we can see read 5 is different for read 2 to read 4. Okay, read 6 to read 0. Read 10 is new array. You can set up a read array on your computer and choose which version you want. But we know read 5 is popular. Okay, modern use of read and ECC. Read 0 has no redundancy. Read 1 is too expensive. Read 2 is obsolete due to on-disk ECC. Read 3 is not commonly used because that input and output rates. Typical model code words in DRAM memory systems. This is some correction, some calculation. Okay, we can see common failure mode is burst of bit errors. Network transmission, disk, distributed storage, contiguous sequence of bits in which first, last, or any number of intermediate bits are in error caused by influx, noise, or by feeding signal strength. Effect is greater at higher data rates. Okay, this is the summary of great idea, dependency by redundancy. So please remember reliability, availability, memory error. You can see timing distance. 2, 3, 4. 2 is parity for single error detect. 3 is single error correction code at encoded bit position of error. 4 is SEC or double error detection. Read has many different flavors, all with their pros or cons. Pros or cons is input and output. Generally, disks are cheap enough that many of them some smart organization here say storage. So read is useful storage. Okay, this is some slides about timing ECC. You can see, but you don't care. Okay, there is lecture 25. So in lecture 25, we must focus dependability and redundancy. So you can find the dependability and ECC. Dependability is important and important knowledge points. So lecture 25 is in this. Okay, lecture 26, we can see there is some powers of 10 view of CS61C. How much have you learned? What's new? We can see there is power of 10 inspired view of 616. There is U2 power of 10 view. So there is the data's origin. and Google's origin WSC, and this is containers in WSC. There is Google server array. So you can see Google is very useful and very famous. Google Rack with 20 servers as network switch in the middle. Array switch connect to racks by multiple 1 GB links. This is the Google server internal. Yeah, in the former we have seen.
Two processors
and some components. Yeah. There is the CPU, Central Processing Unit. In the computer, CPU is important component. We can't design, we can't slice the CPU, but we can use the calculation, the ability of CPU. The ability of CPU is calculation. Calculation is very important for CPU. We want CPU, the ability of CPU become quick and quick. If the ability of CPU become quick and quick, the power of computer is become power and power. Okay, this is processor. You can see there is 3 courses. Yeah, 1, 2, 3. In the middle there is system interface and some cache. So there is some components in processor. There is CPU core. There is some floating point unit, load and store, data center, execution unit, bus unit, instruction cache, and
caches can
align microcontroller and memory controller and level 2 cache. There is from AMD
processor.
Yeah, AMD and Intel are companies for product CPU. Yeah. So we can find this is transistor. So you can find this image is from big to small. Yeah. In above, the image are in whole, are in big, and become small and small. Yeah. And we can see there is transistors. Transistors, you can see average gate each. The size is also nanometer. So this is power of 10 view. How much have you learned and what's new or what's next? We can see there are 6 great ideas in computer architecture. So please remember, please do something for 6 great ideas in our textbook. If you have time, you can look some PPT or look some slides. You can remember, you can recover the 6 great ideas. 1 is abstraction, 2 is Moore's law, 3 is principle of locality or memory hierarchy. 4 is parallelism, 5 is performance, measurement, and improvement. 6 is dependency by redundancy. So there are 6 great ideas in computer architecture. So if you have time, you can look the slides. The next week is the last week.
Yeah.
So in the last 2 courses, we can talk about several interesting topics. For example, machine learning. For example, big data. Yeah. So
cloud computing.
In today we have completed the content of computer organization. So tomorrow or weekend, you you have time, you can do some about computer organization. The examination, I want choose some simple problems from textbook. So if you have time, please read the textbook. Some problems, some examination in every chapter. So. Yeah. There are some exercises in every chapter. So I want to choose some exercises from textbook to complete the examination. Okay. So you can tell the classmates in foreign countries, please tell your classmates to do some exercise in every chapter. Okay. So textbook, there are principle of locality or memory hierarchy. Memory hierarchy is very important in the formal class. The great idea for is parallelism. There is parallelism. And there is performance. There is dependency by redundancy. Okay. The authors give us what's next. We can see database, applications, language and compilers, security, software engineer, and operating system, computer architecture, and embedding system, and digital system, design. So you can see there is some symbols, some terms for the next class. Okay, CS 161 is security from the Stanford University. This is CS 162 operating system, and there is CS 164 compilers and programming language. There is CS 168 networking. There is CS 186 database. There is CS 152 computer architecture and design. So this course is related to CS 661C. Okay. There is another course. Okay. There is all content. And thank you. Thank you for your patience and studying.